This video introduces optimization problems and how to use calculus to solve it. So optimization problems are just application problems that require a quantity to be maximized or minimized whilst being subject to various constraints. A good example would be, suppose you have a rectangle that's inscribed inside a semicircle of radius 1. What's the largest such area that that rectangle could have? Now I'll solve that problem as I explain the general method. So the general outline to solve these problems is actually mostly pre-calc. The only very end is when we use calculus and use a derivative of some kind. So the first thing would be is to read the problem until you understand it. That means, do you know what's given? What are unknown quantities? What's the thing you're trying to optimize? If you're not sure, or if it helps you, draw a picture that represents one particular instance that could be possible in your problem. If you're still unsure of even how to start, just guess at your answer and see if that would be the optimal value. It would probably not be, but it's a good way to go about starting the process of how to model the situation. So for example here, if I have a semicircle centered at the origin and above the x-axis of radius 1, I have put in for you already a rectangle subscribed in it. That means it's as large as it possibly can be and still be contained inside the object. And it has a certain height and a length. Let's say I have no idea what would be the dimensions of this particular rectangle that would maximize the area of that rectangle. So obviously the rectangle would be symmetric. So there's a certain length and a certain height. But just by looking at it, you can tell that this distance here, if I knew that distance, I could then double it and get the length. So the overall maximum length would have to be less than 2, as this radius is 1 and that radius is 1. So the length must be no more than 2, but it's got to be at least 0. So I'll guess and say, I think the length is 1. And that gives me the maximum area. That's probably not true. The height then would then be found in terms of this length. Because if this distance is 1, then this distance is a half. That means this point on the graph has an x-coordinate of a half, and I can find the y-coordinate by solving for y in this formula when x is a half. That would give me that the y is 3 halves. And you recognize that the y-coordinate of the point is actually the distance the point is from the x-axis. That's the height of the rectangle. So the height of the rectangle is the square root of 3 over 2. So the area of my particular guess would be the square root of 3 over 2. Now, is that the largest possible area? No. You can find a different length that would give you a different height. That would give you an even larger area. So this is not the answer. But it does encapsulate everything you need to know just with numbers that will help us in the next step when we go about formulating with variables. Now we enter into the next step, which is to introduce variables in order to have a representation of the thing we're trying to maximize. So first, we assign a variable to the quantity that we want to maximize. In this case, the area. We also assign a variable to any quantity that affects the thing we're trying to maximize and minimize. In this case, length and height. But you might also want to write those things in terms of other variables. Now notice in the problem, in the end, I looked at a certain point on the curve. So let's focus everything in terms of that point. So that point would have an unknown x and an unknown y. I know, though, that since that point is on the circle, that x squared plus y squared would equal 1. So I could say that I will optimize the area. The length then, in terms of that point, the length would be 2 times x. The height would be y. That means the thing I'm trying to maximize, being the area, would be 2 times that length, 2 times the x, times y. So the area is 2x times y. We also have a constraint that x squared plus y squared is equal to 1. There's also some understood limitations because this point in the end must stay within the first quadrant so that this rectangle has any meaning at all. After all, if this point is suddenly over here in the second quadrant, the x would be negative, and that means the length would be negative. That wouldn't make any sense. So there's an understood limitation that x is more than 0 and less than 1 because of this point and that point. Also, if I wanted to, I could allow x to be 0 or I could allow x to be 1. In those two extreme cases, there wouldn't be a rectangle at all. One of the dimensions would actually be 0. But that's okay, because I'm trying to find the maximum area. And if one of the dimensions is 0, the area of that object would be 0. And so that would certainly not be the maximum area. So for this problem, I will also include the endpoints, even though the endpoints don't make a whole lot of physical sense. The fourth step. Our problem currently is that often when we get to this stage, the variable we're trying to optimize is in terms of two variables. Like in my case, x and y. That means a is a function of two variables, and we just don't know how to deal with that yet. So I want to convert it to be a function of only one variable. So I remember, though, that x squared plus y squared was equal to 1. I could then solve for y. To get y is the square root of 1 minus x squared. So that the area would then be 2 times x times the square root of 1 minus x squared, because this was y. Now that I have that, notice that the domain, though, as I mentioned before, can only go from 0 to 1. And I will also include when x is 0 and when x is 1. I now want to know what's the maximum value of this function, our area function, on this interval. Notice that it's a continuous function defined on a closed interval, so we know how to find the maximum and minimum values of that function. We already did that earlier on in the course. The fifth step is to find the critical points and determine the maximum of the function using the different tests we know, either first derivative test, second derivative test, or using the fact that we know that for a continuous function on a closed interval that there's required to be a max or a min. So here we'll go about finding the critical values. We do that by taking the derivative, which you see here, and I simplified it to be a nice simple fraction for you. We then have to set that equal to 0 and find out where it doesn't exist in the interior of the domain. Now, if it's at the endpoints or outside the interval, we'll just ignore them. I solved the equation when the derivative is 0, and I got two answers, only one of which, though, is inside the interval from 0 to 1. And the derivative does not exist if x is 1 or negative 1, but only one of those actually lies inside the interval. So I only really get one critical number. Now, since we have a continuous function on a closed interval, I just evaluate the function at the endpoints and at the one interior critical number, and the largest value is the answer. So in this case, the area is maximized when x, remember that's half the length, is equal to the square root of 2 over 2. The sixth and final step is just make sure you answer the question. So the question was, what was the dimensions of the rectangle? So since x is half the length, that would then mean that the length is the square root of 2. And since I know what x is, I can find out what y is. In this case, y would actually also be the square root of 2 over 2. And that'd be the height. So the rectangle, the largest such rectangle that maximizes the volume and would be inscribed in the circle, its length would have to be the square root of 2. Its height would be the square root of 2 over 2. So in general, these are the steps we use. We first read the problem in order to try to understand what needs to be optimized, and also think what types of things as they change will affect what we're trying to optimize. Then if we're not quite sure, we draw a diagram to help us out, and we sometimes guess at a solution. By guessing at a solution, we never actually get the optimized value. And even if we did, we wouldn't be convinced that it's the right answer. The next thing would then be is introduce variables. Now by guessing, you're actually going to go through the same process with the variables. This would then write down all the ways to express the variable you're trying to optimize in terms of others, and also to write down any equations that restrict the variation in the remaining variables. That's called the optimization equation and the constraints. Step 4 is to take the equation that expresses the quantity to be maximized or minimized in terms of only one variable. Oftentimes right now it's in terms of 2 or 3 or maybe more. You want it to be a function of only one variable. And then you have to think about, in the context of your problem, what would be the domain of this function. The fifth step is basically just use calculus. Now, for that function, you'll have a domain. You want to know its maximum and minimum. So use the first derivative test or the second derivative test, or use what I showed you before for continuous functions on closed intervals to figure out what the maximum should be. The final step is just make sure you answer the question. Sometimes the quantity for the variable that optimizes your quantity, that variable is not actually the answer. It's something else. Like in my problem, I gave you an x value to maximize the area, but x wasn't the answer. It was the length and the width. Now, I'm going to go through many other problems. You can tell that these problems take a while to do. So I'm going to stop doing PowerPoint presentations. Instead, just go to a writing board and write them there instead. So let's try this problem. You must design a rectangular poster to contain 50 square inches of printing with a 4-inch margin at the top and a 2-inch margin on the sides. What are the overall dimensions that would minimize the amount of paper used? Okay, so for a problem like this, let's just draw a little picture. Let's suppose that we have, here's our piece of paper, and then we'll have margins to it. Excuse my drawing, I know it's terrible. So that this distance in here, that's the 2 inches, and the inches over here, this margin is 2 inches. The margin here, that's 4 inches, and the margin on top, that is also 4 inches. Okay, now what I don't know is the dimensions inside. So let's say that this distance is x and this distance is y. So we have at least one constraint. I'm trying to maximize the overall amount of paper. I'm trying to minimize the amount of paper used. So I'll say that's A. A will then correspond to the area in squared inches of the sheet of paper. So I have x and y are the interior dimensions. Of the text space. And that's also in inches. Well, obviously then, let's see, we have to have that the amount of area used for the whole paper, that would be this distance from this edge to that edge. So that is 2 inches, x and 2 inches. So that would be then total so far, x plus 4 is one dimensions of this piece of paper. And the other one would then be y plus 8, using the same idea, just adding from this edge to that edge. So you'd have 4 and 4 and y. So the area then is x times y plus 8x plus 4y plus 32. But I have a restriction that the amount of space for my type has to be 50 squared inches. So that means that x times y, the amounts, the rectangle inside, that has to be at least 50, and let's make it be 50 so we use as much space as possible. And that'll be in squared inches. So this then is the beginning of the formalization. What I need to do then is somehow write the area in terms of only one function. So notice though that x times y, we know what that is, it's just 50. So the area so far is really just 8x plus 4y plus 82. Still, the area is a function of two variables. So I'll get rid of the y by coming back over here and noticing that y must be 50 divided by x. So I'll replace that right here to get 400 over, oh, that's not right. That's not right. I'm replacing the wrong one. To get, let's try that again. That 8x plus 4y, and the 4y would then be your 200 over x, because y is 50 over x, plus 82. And that then gives you, then the area being used as a function of two variables. I want to then go and try and make this be a function of only one. What the hell am I saying? I already said it twice. I'll have to edit that. So what I want to do then is is now find the domain of this function. Well, clearly, just because of this, the x can't be 0. But, I mean, obviously in the picture, x can't be 0. Because if x is 0, then we don't have any space for our type. So x can't be 0. Also, x and y both clearly must be positive. So we have a restriction that x here must be at least bigger than 0. Now, an interesting thing would then be is, well, could it be any number I like? Could x be, say, 1,000, 2,000, 3,000? And yeah, actually it could. It would just be an incredibly long piece of paper that its overall height would be really close to 8 inches. So there is no upper bound on what x could be. So this is a continuous function on the interval I gave you, but it's not on a closed interval. So I'm not guaranteed there's a max or a min. To find the max or min, I'll then just take the derivative. So the derivative of this function would wind up being, you'd have 8 minus 200 over x squared. I will, as I normally do, I'll just go ahead and solve when is that derivative equal to 0. Now, when you do that, I have to scroll the page up a little bit. That would mean then that 8 minus 200 over x squared would have to equal 0. But that would then mean that x squared times 8 minus 200 would equal 0. So 8x squared would equal 200. So x squared would then equal 25. That means x is plus or minus 5, but only one of those numbers, 5, is in the interval I'm interested in. Of course, I'd also find everywhere that the derivative does not exist. So I'll find all x so that the derivative does not exist. Now the expression for the derivative, though, is 8 minus 200 over x squared. The only way this would not exist is if this denominator would be 0. But that's 0 only if x is 0. And x is not in the interval. So we ignore it. Now that I have all my critical numbers, I'll write down the interval that represents the domain. So this is 0 to infinity. I'll put the first derivative above this line. On the line, I'll put the only number where the function exists and where the derivative is 0 or doesn't exist. And that's at 5. And then just check numbers. Take a number bigger than 5 and plug it into the derivative. If you take some number larger than 5, like a billion, and square it, and then divide it into 200, that's really close to 0. So the first derivative on this interval will be positive. And doing the same thing, if you just plug in 1, you'll see that the derivative on this interval is negative. So we know the function decreases and then increases afterwards. And since the function is continuous at 5, I know that a of 5 is a relative min. But it's the min of the function, because the function value always decreases until x is 5 and then always increases afterwards. So a of 5 has to be actually the minimum of the entire function. Now don't forget, we had to answer the question. The question was, what are the dimensions of the paper? So the dimensions of the paper are that the x is 5 inches and the y was, well then if x times y is 50, then y is 50 divided by x, that's 10 inches. The dimensions of the paper going this way was 4 more than this. Remember, it was 2 inches, x, and then 2 inches. So the paper is, that'd be 9 inches by, and the remaining length was 4y and then 4. So that's 14 inches. So this piece of paper should be a 9 by 14 piece of paper, and that will then minimize the amount of paper used and yet still allow 50 squared inches of space to write in, keeping into account the margins as I've given them to you. So this time I'd like to find out if the number of passengers on a bus tour is exactly 30. The bus company would then charge $30 per person. But the bus company also, for every additional person, the price of all the passengers is then reduced by 50 cents. So what's the number of passengers a bus should carry in order to maximize the company's revenue per bus? Well, to do that particular problem, what we'll do is we'll say that A then will correspond to the amount earned per bus. And X will be, that'll be the additional numbers. Of passengers. And P will then be the price per person. So the amount earned by the bus should be the number of people, which would be X plus 30, times the price per person, which is P. This is obviously no good. I need a function of only one variable, but we know that the price per person starts at $30 and goes down by 50 cents per person. So that means that I can find that the amount is then really X plus 30 times 30 minus 1/2 X squared. Oh, X squared, I just did the multiplication. 1/2 X. There we go. So I'll just multiply this out to distribute that product. That will then give you a negative 1/2 X squared. You would then have 30X and minus 15X. That's plus 15X. And then you'd have plus 900. That is the revenue. Now notice the equation is a quadratic, which suggests that as X increases, in the end this term will dominate and the revenue will go into the negatives, which obviously we don't want to do that. So here this only makes sense for this particular bus as long as they're actually charging their customer something. So the X is going to be at least 0 because X is the additional people. But X can't be too big. In fact, if X is going to be, let's say, 60 or more, once we get to 60, the price per ticket is 0 or less. So we'll insist that the number of people is 60 or less, even though if we take 60 people, the actual bus ride's free. So let's see. Now that I have the function to be optimized and the domain, I'll just use some calculus. So let's go ahead and find the derivative. So your derivative would then be negative X plus 15. I'll then solve that the derivative is 0 for X. So then negative X plus 15, that would be 0. So X would then be 15. Well, but if that's true, that would then mean that if you look at the domain, which would be only from 0 to 60, in that domain, I get only one critical number. Now notice I skipped the step where the derivative doesn't exist because the derivative is a polynomial. It always exists, doesn't matter what X is. So from here, we would then test the intervals. Although, since the function is defined on a closed interval, I don't need to test the derivative signs. I just do the evaluation method instead. But I'll go through this anyway. So between 0 and 15, pick a value and plug it into the derivative. Let's say you pick 2. Then the derivative would then be positive. If you pick some number between 15 and 60, like 16, the derivative would then be negative. So the function is always increasing and then decreasing. By the first derivative test, this corresponds to a relative max. But while this is indeed a relative max, and that's by the first derivative test, I also notice that the function is always increasing as X increases over the interval from 0 to 15 and always decreases after it. For that reason, then, it can't just be the relative max. It's the maximum. So the revenue, your maximum revenue, is A of 15. Whatever that number is. You just plug 15 into the quantity in order to, in your function, to find out what that maximum revenue equals. But we didn't want that. We wanted to know the number of passengers on the bus. So the number of passengers is the 30 we start with plus the additional 15 people. So we need 45 people to maximize the revenue. And that's it. And that gives you a basic introduction to optimization problems and solving them with calculus.